This is our last subject on kinematics of particles. We're going to study constraint motion of connected particles. So there exists more than one particle here, but these particles are connected to each other. That means they are interrelated, and this relationship is a result of the constraint imposed by this connection. Uh, in these cases, we need to account for these constraints. We need to write in a constraint equation, and you'll see that this constraint equation will help us to investigate these type of systems. In the next year's course, machine theory, you will also visit these type of constraint equations when investigating 4-bar mechanisms, for example. So this is basically the foundation of that type of investigation. Now here we're going to start off with a single degree of freedom case, 1 degree of freedom case. That means there is only one way of motion in this type of mechanism, if we would call it like that. And this mechanism is composed of pulleys and cables. And here you see an example to understand the concept. We have this particle A and then particle B connected to each other through these cables and pulleys. There's a single cable here. And the assumption that you would have in this case is that the cable length L is constant. It's not going to change. It's not flexible, although nothing is that rigid. But here we have the assumption that this L is constant. It's not going to change. And then we have these pulleys, the first pulley, second pulley here, and here we have this displacement of a particle defined as an x distance from the center of the pulley, second pulley, and from the center of the first pulley, the location of this pulley is defined with respect to the center of the second pulley by y distance, and if you would like to talk about this, b is the constant. This constant length is the difference between this connection port, which is the ground, with respect to the center of this pulley. Now, if we say this L length is constant, then it is composed of this x plus y plus b, and then the amount of the length of the cable around these pulleys. This is 1/4 of the pulley, the circular part, and this is just half of the pulley. So as a result of that, we have the half of the pulley length, PR1, pi R1, and then this is the quarter of the length of this cable around the pulley, which is pi R2 over 2. Now, this is our constraint equation, but the variables here are x and y. Other than that, the other things here, R2, R1, and B, they are not variables. They are fixed parameters. Now, if you take also L is a fixed parameter, that's our assumption. Okay? If you take the derivative of this equation, and this is our constraint equation, by the way. Now we have written a constraint equation, and the constraint equation is about the length, which we assume that is constant. If you do the derivation with respect to time, as we have already pointed out, these two are the variables. They are changing with respect to time. The resultant will be 0, that is equal to x dot plus 2y dot. Now we have a relationship as a result of this first derivative between the motion of this A particle and Y particle. B particle, A particle and B particle. So I can call this x dot as velocity of A and then y dot as the velocity of B particle. They are interconnected. So velocity of A is not independent of velocity of B. They are related to each other, and this relationship is through this constraint equation. If you take one more derivative of that, you'll find out the acceleration equation that is relating the acceleration of particle A to particle B. So we get this information of the relationship between these two particles that are in constraint motion. Let's take a look at a 2 degree of freedom case. Now we have two possible independent motions here. And in order to have that, obviously you need two cables. Now here is the first cable. Maybe I should draw it with the green line. Okay, this is our first cable. Round up to y, and this is the total length. So we need to write a equation for this first cable L1 that is composed of YB. Then this length is YC. We have YB, YC, and then the rest from this center to the D point is YC minus YD. And then you might ask yourself, well, why didn't we consider this length of the cable around the pulleys? The reason is that it is a constant. What I'm going to do with this constraint equation is I'm going to take the derivative of it and the constants will go away. So I can just have these parts as constants. So what is inside here is the length of the cable around these two pulleys, basically. Okay, and then we can talk about the second cable, and the second cable is this whole cable around going around here and then up to point A. Now we can just neglect this part here, which is constant again. Okay, and the total length of the cable in that case for the second cable is YA plus YD, this length, and then another YD. Okay, this is the other YD length, and plus some constants. And as a result of that, now we have two constraint equations, 2 degrees of freedom. And if we take the derivative of these two equations with respect to time, then we get the velocity level equations. And in the velocity level equations, you see that we have y dot b, y dot c, and y dot d. And also we have in the second equation y dot d and y dot a. Now if you want to relate these two equations, well, there is a relation point yd. You can represent any of these equations in terms of yd dot and then place that information in the in one of the equations. So you will combine these two equations if it's going to work for you for your problem. If you take one more derivative, then you'll get the acceleration level equations. Okay, so depending on your need in your problem, you might want to combine these equations. Let's take a look at this example. Now, how many cables we have? We have one cable here. Okay, this is the first cable. And then we have another cable here. Here. So this is a 2 degree of freedom case, and as a result of that, we have two independent parameters here, xa and xp defined, and then the motion of both of these will define the motion of this particle. And what is asked is the upward velocity. Okay, so we are interested in this upward velocity of this m. But when you take a look at the way that this y2 distance is defined, it is in the downward direction. So we are interested in the velocity of this mass, and that will be negative y2 dot in that sense, in the negative direction, because the upward velocity is asked to us, not the downward. If it was downward, then we would have the positive sign. Now all we need to do here is to write out the two equations, two constraint equations that will composed of xp for the left one, and for the right one that will composed of xa. So depending on which one you write, so let's write the yellow one here, L, sorry, the green one, the yellow one, L1, let's call it, that will be composed of, oops, sorry, wrong location, xa plus y1 plus basically y1 again, and then you can write out the equation. I'm having a hard time seeing my cursor. Okay, for L2 that will be xp, and then plus y2 for this length here. I'm just neglecting the constants here. You might want to write here a constant that will disappear. These are the cable around the pulley. And then here we have xp, there's y2, and there's also this part which is y2 minus y1. Okay, so here we have two equations. All we need to do now is to take the derivative of it, and then there is this information about y1. So from this equation I can relate y1 to xa. Then I can make use of that information here, substitute the y1 equation as a function of xa, and finally I will get an equation for y2 which is a function of xp and xa. But that's the way to solve this problem. You have it already available. So this is our first equation, xa plus 2y1. This is our second equation. Take the derivatives. Now you have this y1 that could be written as a function of xa, and then there is our y2 dot equation which can be written out as a function of y1 and xp. Now as I have this y1 already as a function of xa, I'm just going to plug in that information in the second equation so that I will have this y2 dot as a function of xa and xp, which is already given to us in the problem, by the way. Both of these cables A and B is given with a velocity of 2 meters per second to each side, so we know that information of velocity of A and B. And as a result of that, firstly we find this y1 as a function of xa, substitute that information into the y2 equation, and then as a result of that we get this upward velocity as the negative sign of y2 dot, which we found 1.5 meters per second for these given speeds of xa and xp, or ab cables. Okay, let's take a look at the other example. In this example, now we have a single cable, that means single degree of freedom for this type of question. The cable length we consider again is the same. Another thing that we neglect here is the diameter of the small pulley. The main reason for that is that in the previous examples, the cable around the pulley, the length of the cable around the pulley doesn't change, but in this case it's gonna change. Why? At some point of the manipulation, this will come around here, and then if you take a look at the amount of cable around this small pulley, it has become smaller. The amount of length of the cable has become smaller, so it will vary. And if we just neglect the size here, so we say it's almost dimensionless, as a result of that we can do this assumption. So L is the total length is composed of, if we call this y distance, and then a function of x and h. This is x and this is h, and from the square root of x squared plus h squared we find out this distance. Okay, this is the square root of x squared plus h squared. Plus y is the total length of this L, and this is our constraint equation. This is the constraint equation. Now after this point on, all we need to do is to derive that with respect to time. If you do this derivation, then we find this y dot. What the question is asking us is the total velocity, determine the magnitude of the total velocity of B. Now B will have two types of components of velocity. One of them is in the downward direction, so there will be y dot, and there will be also x dot, because as it is moving downward, we expect that this car here is going to move in this direction, in the negative x direction, as this is moving down. Okay, so it's going to have two components. It will have an x dot component and y dot component, and in order to find the magnitude of the velocity of B will be a combination of these velocities in the x and y directions. Okay, let's move on. After this derivation, now we already have this x dot available to us. This is the velocity of A that is available to us, and we know that it will be in the negative direction. So it is negative VA in that sense. And y dot, we have x dot here, so we're going to substitute that with the velocity of A point, or as this is a single rigid body basically, it's and then it's not doing any rotation. We're going to talk about these in the later lectures as well, but in a rigid body that doesn't do any rotation, the velocity that you're going to measure at any point will be the same. So the velocity of the cart or the velocity of point A is given to us as VA in the question. And we are trying to find the velocity of B as a function of VA basically. And here we have the y component of the velocity of B particle, and there we have x dot. We're going to exchange that with the velocity of A, and as a result of that we find the velocity of B as a function of the velocity of A. And the assumptions we had over here is based on the cable's length being constant, it's not flexible, and then there's this small pull. So we were able to obtain the velocity of B in terms of velocity of A in this question.